Hi, thanks for watching this video. For the past year and a half, I've been processing Seestar S50 data, and now I'd like to show you what I learned. Today, I'd like to share my complete workflow on how to make the most of what this smart scope can capture, using only free and open source software. Yes, you can still achieve great looking results even without PixInsight or other paid tools. You just need to understand what each tool does best. In this video, I will not just give you step-by-step instructions. I'll explain the reasoning behind every choice, show different approaches for different situations, and demonstrate common processing mistakes that I used to do as well that can degrade your image. This is not a quick click here and there tutorial. It's an in-depth guide to help you understand your data and the software you will use. Of course, if you have feedback or corrections, feel free to leave them in the comments so we can all learn. Today we're processing NGC 2237, the Rosette Nebula, captured with a Seestar's dual band filter in mosaic mode. I chose this target because it lets me show a comprehensive workflow, efficient mosaic stacking in Siril 1.4, dual band emission extraction for H-alpha and O3, and the full processing pipeline. I'll also reference other images occasionally to show how the workflow adapts. Now quickly, let's see the software that we'll use in this video. We have Siril 1.4.0, the latest version. This is the software that we use for pre-processing, so stacking and post-processing. Here you can also see a list of the Python scripts that we'll use. You can pause to read it. Then we'll use SETI AstroSuite Pro, which is another important program. We'll use this program for mainly masks because Siril doesn't have them for now, but this may change in a future update. Then we have the optional software, like Darktable and GIMP. This is software that we'll use later in the process to apply final adjustments. All this software is free and open source and available on Linux, Windows and macOS. So here we are in Siril 1.4.0 release candidate 2. This is very close to the final stable release of 1.4, so nothing from this video should change from that moment. So before we jump right ahead into stacking, I want to make sure that the beginners that are watching this video that might not be familiar with Siril's interface actually start from the very basics before stacking. So we're gonna start from the UI to opening a single raw frame from the Seestar. So first thing we see is the console that contains vital information about the program when it launches. We are going to explore this later. And there's this panel that you can drag and resize. Then there's the conversion tab that we're going to use later for creating a sequence. The sequence, calibration, registration, plot and stacking tab. We are all going to see them in detail later. So all that you have to know is that here you have this tab that you can resize, the console, and this is the area of your image. The tools here are organized in these drop menus: image processing, tools, and scripts. So before we go further, let's show you a raw exposure from the Seestar, one single exposure. This is a fits file, so let's open it real quick. Let's auto stretch it. And now here, if you've never seen a raw Seestar exposure, you may be confused. Why is it in black and white? Well, this is a monochrome image. This is actually a raw exposure from the Seestar. Now, if you've only seen the exposure how they look on the Seestar app, you'll notice that there are already colors. There are already colors because these images are just JPEG previews. This is the real deal. This is the raw fits files. So if we zoom in, we can actually see that there's this checkered pattern. This is called a Bayer matrix. So basically, every pixel here, based on its intensity, its value, and its position, represents one single color. So let's see it like this. The Seestar, like many other cameras that we commonly use, like for example in smartphones, are OSC cameras, one-shot color. So basically the sensor, we can say the well that captures the photons, has many tiny pixels. Every pixel on top of it has a filter, and those filters can be red, green or blue. So depending on what filter every pixel has on top, it'll be sensitive to mainly one color in theory. All the pixels with the tiny filters on top is called a CFA, a color filter array. Once we have that, the program, for example Siril, uses the Bayer pattern to then later demosaic the image, so turn it into a color image based on the position of the pixels and its neighbors. So another very important thing that makes feeds files special is the feeds header. So here we can see the header, and basically it contains many vital information for the program to process the image. Now you can see we have many keywords here, but there's only a few that you normally have to understand. So we have, for example, the telescope that we use, the filter, the program, the date where the observation, the phase file was created, the exposure, so many useful things, including the focal length that Siril actually pulls this information from the feeds header to automatically compile some fields. We have also this very important, it tells us the type of Bayer pattern, which in this case for the Seestar is GRBG. You don't have to worry about this because Siril will choose this automatically. And you have tons of useful information. This will also be useful later as we place solve. So also a very important thing, if you plan on sharing your feeds files, these are sitelat, sitelong. These keywords actually contain very precise geolocation coordinates. So make sure you actually edit them into 0 if you don't want to give away your precise location. You can actually edit the keywords from this header editor part. You can also add or remove them. You can of course click and save them like this. Of course there are some keywords that cannot be edited, and also these are all the ones you read basically. And these are all the keywords that can be edited, but be careful while editing, because that could make if you edited the wrong way, it could make the feeds file unusable. So here, when I apply the auto stretch from this menu, I actually didn't do anything to the image. I didn't modify it in any way. This is just a way to visualize the image in a way that the data is visible to us, but the real image looks like this. So here, I simply changed the visualization from auto stretch to linear. This is the linear image, just as it came from the Seestar's camera. But why is it linear? So let's look at the image, and we can see that there's either very bright pixels or very dark pixels. The stars are very bright, while the background where the nebula lives is very dark. At its core, a pixel is just a number representing a brightness level. An image is simply a two-dimensional grid of these values. You arrange them all together and you get an image. This specific image is linear. It means that the value of every pixel is directly proportional to the amount of light the sensor has received. That's how digital sensors generally work. So for example, if the amount of light received doubles, the numerical value doubles as well. The human eye, however, does not work this way. We perceive light in a non-linear way. We are far more sensitive to changes in low brightness than in highlights. This is why a linear image looks meaningless to us. The contrast range is too extreme for the brain to process. There is just a very big difference between the brightest pixels and the darkest pixels. The data is all there. We just have to transform or stretch those numbers into a nonlinear state to make them meaningful to human vision. That's where the auto stretch comes to the rescue. It transforms the value of the pixels in the image to finally make it visible to us. But, and this is important, it does not change the underlying data. We did not delinearize the image just yet. This is useful to see what we are doing when applying processes that must imperatively be carried out on a linear image, such as color calibration. So if we pull out our histogram here, we can actually see it. If you're not familiar with what an histogram is, it is basically just a two-dimensional graph showing all the pixels in our image related to the brightness levels in the image. So the x-axis, the horizontal line, starts from the very left, showing where the darkest levels live, while on the very right it shows where the brightest levels live. Then here we have this very steep hill. We can zoom in using the plus button to see it better. Zooming in right here, we can see where most of our data lives. This mountain is comprised mostly of sky glow, the natural and artificial brightness of your background sky. So if you follow the mountain slope down to the right, you start finding the actual signal from your target. as the line flattens out further to the right, that's where the stars live. You won't see massive peaks there because stars only occupy a tiny fraction of the total pixels, but that's where the brightness is recorded. So now let's look at the left side of the histogram. You'll notice a flat line, so this gap between the wall and the start of our mountain. This is the black level, also known as a pedestal. This is a deliberate amount of value the camera adds to every single pixel to ensure none of them drops to zero or a negative value. If the mountain were smacked right against the left wall, we'd have clipping, which means losing the faint details. By shifting the peak slightly to the right, we ensure all of our data is safely on the histogram. What we are going to do later is that we are going to stretch the histogram. I want you to visualize it metaphorically by imagining that you take the two ends of this eel and you pull it. You can imagine it that we are stretching the histogram. So what this means in practice is that we are going to compress our dynamic range. Basically it means that values that were previously, pixels that were previously very dark are going to be transformed with their value becoming much higher and finally visible to our eyes. We're going to do this later. If you want to return to the normal visualization, you can press this button. Now for the other basic buttons in Siril, you have the rotate buttons that can rotate your image 90 degrees, clockwise and counterclockwise. You have the mirror buttons, mirror vertically and horizontally. As you can see, every modification that is applied to the image will be logged into the console. This is one of its functions. By using this button you can export the log in case you run into any error that maybe you want to report to the Siril team. You can do that. You can also clear the log. The stop button is useful when you're running an operation and you want to stop it, so maybe you're running stacking, anything, you can stop it at any moment. Then there's the command line that you can use to run some operations without having to go through the GUI, which is very useful. I'll try to show you some commands later, but you can also type help to see a list of all the commands that you can run. I'll try to show you some later, but if you want to learn more, I recommend you read Siril's documentation, which is very detailed on this, and it shows you some very practical examples. So then you have these other bottom buttons that you can use. For example, this is to fit the image to the window. This is to show the image at its normal size. And this button that we can use later, this is to open the frame list of the current loaded sequence. There is no sequence loaded right now, so there are none. Quickly let me show you some other tools, like in tools image analysis, aberration inspector that you can use to quickly preview your image to see to watch for distortions. This basically compares the center of your image here to the sides. This is useful because, for example, here you can see that on the side you have weird star shapes, which is normal for the Seestar for its tracking errors. So we've done this quick introduction to Siril's interface. Now we can finally begin stacking. We can begin our pre-processing workflow. So I see that many people in Siril stack using scripts. So scripts like the OSC pre-processing or an astronomy script for smart telescopes, which is absolutely fine. These scripts are fast and efficient. But for a beginner, if you're learning to stack for the first time, I don't recommend starting with scripts because in their automation they hide a lot of the process, and so you end up with a final stacked image and you don't know what was done to it, the frames that were rejected, what the script is doing, the settings that it is using. So I think that the best way is to first stack yourself manually to understand how everything works, to look at your frames, choose your settings, understand what they do. And I know that it might look intimidating at first, but I promise that stacking manually through Siril's own interface is really quite easy. It is well logically laid out, and now I'm going to show you. So this is the first tab that we are going to use, but before that let's set home directory. The home directory is the directory that Siril uses when we load the frames into the conversion tab. It'll create a sequence. The sequence will be saved inside this home directory, and also inside the home directory it'll save the registration files that we'll see later and a few more things. So the home directory is important to set to keep your workflow organized. So to set your home directory, you go onto this home button, you can click on it, and I already set mine, but in case you wanna set it, you go to where your folder is, you go inside of it, and then you click open to set it as your home directory. So now we're going to load our frames. So this is a way to load your frames. You drag and drop them into the conversion tab. This works, but you can also use the plus button and go to the directory where you have all of your frames and select them from here. So if you want to remove one subframe from the list, you can select it and use this button. It'll remove the selected subframe, or if you want to remove all, you click this button, remove all files from the list. It'll remove them all, so let's put them back in. So finally, let's give our sequence a name here. For example, Rosette Nebula. Okay. So here we can also set the suffix that every file that will be created is going to have. So for example, here it's set at 1, so it's going to be Rosette Nebula 1, Rosette Nebula 2, Rosette Nebula 3. You can edit this, but default is fine personally. So also here we have this drop menu that has all the types of sequences that we can create. The main ones that we're going to use is fits images and fits sequence. So fits images means that it is going to take the original images and then it is going to duplicate, so create a file for each subframe in the fits format in the new sequence. But if you want to avoid having a ton of files, so maybe for organization or things like that, you can use the fits sequence format. So all the new fits files will be put into one single file, one big file called a fits cube, and this is also pretty convenient. But keep in mind that the fits sequence format momentarily does not work with the astrometric alignment. This may change in a future update, but for now just keep in mind that it doesn't. So the fits sequence format is actually quite useful on Windows because there is a limit to how many files you can have open at once on Windows, which is 2048. So if you want to create a sequence on Windows that it is longer than 2048 files, you're going to use the fits sequence format. But always keep in mind that if you're planning to do a mosaic, that won't work, and so you may want to split your stack into multiple batches and then stack the masters from each. So once we got that, then here we also have this two option. This is the symbolic link option. So basically, as it says here, it means that if your original exposures are already in the fits format, which in the case of the Seestar they are, instead of duplicating the files, it is just going to create a symbolic link in the new sequence. So it means that it is a file that points to the original exposure, and so this can save disk space. So for the sake of this tutorial, I'm not going to enable this option, just to show you what happens inside the Siril home folder that I've set. Also, as it says here on Windows, it requires extra work for this option. Then we have the debugger option, which, as I've said before, this is what turns our CFA images into color images, so it demosaics the images. But we are not going to check it just yet because we are going to use Drizzle in the registration tab over here later. And Drizzle has its own demosaicing algorithm, so if you plan to use Drizzle, do not check this option or else it won't work. So now let's click on convert and watch as the files get converted into a sequence. Okay, so conversion was completed. All of our files have been successfully converted. We can click the frames icon in the bottom right to open the frame list, and now we can browse them. These are all the frames in the sequence. We can select or unselect them. We're going to see this frame selector better later as we register our frames and as we're going to inspect and sort them based on their quality, on different criterias. So actually now let me show you what happened inside the home directory that I chose. So all of the files have been put here from Rosette Nebula 1 all the way to the end. And then there's this .sec file. So this is the file that contains all the information about the sequence. So it stores statistics about all the frames, about the sequence itself, so registration, how many frames were selected of the sequence, and still in the home directory we can see that a new text file was created, and if we open it we can see that this is a conversion list. So basically it tells us what each of the original fits files to what new file in the newly created sequence they were converted to. So if you want to trace back a converted file of the new sequence back to its original file name, to its original path, you can use this list. Let's go into the sequence tab, and here we can see the name of the currently loaded sequence, and we can use the search sequences button, and Siril will scan for all of the sequences that it can see on the home directory that we have set. So as long as we have the files, the fits files, and the .sec file that contains all of the statistics and information about the sequence, Siril will find the list of sequences, and you can reload it even after closing the program, as long as you have all the necessary files. So here we have always the option to open the frame list like we did from here, and we have the option to clean the sequence. And basically if you have done any operation to the sequence, so you have unselected some bad frames, or if you have done registration to it and you want to start clean, reset the sequence to its default state, you can use this option to clear the data. You can also decide what data is cleared from this drop menu. So here we also have the option to export a new sequence out of the currently loaded one. So for example, if we have selected only the best frames that we want into this sequence, we can export a new sequence with only the frames that we want. We can give it a new name, as you can see. We can choose the format of the new sequence, and we can also check if we want the normalize image checkbox. That helps if we have uneven background illumination caused by varying exposure times or different light pollution levels. So once our sequence has been created, we can finally go to registration. This is when we take all of our subframes, we establish a reference frame, which is the image that all of the other subframes are going to be stacked onto, aligned to, using the stars that are going to be detected by the algorithm. And so this makes our star alignment our registration, which is the step before stacking. So since these subframes have been taken in a mosaic formation, so using Seestar's mosaic mode, we're going to use Siril's new astrometric alignment feature as the go-to for this dataset. But I also want this tutorial to work for if you have taken subframes without using mosaic mode. So I'm going to show you the standard way of registration of a sequence by going right here in the registration tab. So let's start with that, and then we'll go over to astrometric alignment. So these settings, you could pretty much leave them all like this, all at default. It'll work fine, but let me go over it real quick. So this is the registration method. Global star alignment is the go-to algorithm for deep sky images, so just leave this at the global star alignment. All the other algorithms are more simple or suited for planetary imaging, so they are totally different. So the rest here we have transformation. Still leave this at the default, which is homography, which is this most complex type of transformation that accounts for the normal distortions found in real subframes, real photos that always have some distortions. So to align them to one another, you have to apply a more a more complex transformation to wrap the images on top of each other metaphorically, so just leave it at that. Then I recommend you check two-pass registration. So this means that when you click register, instead of registering the images all in one go, it is going to detect the stars first and write the registration data into the .sec file, into the sequence and the subframes, so that we can take a look at the statistics later, at the quality of the image. And then after we have looked at the subframes, rejected the bad ones, we can apply the existing registration, which is actually the same exact step that follows after you have done the astrometric alignment, and then we can go to the stacking. So then we also have the minimum star pairs. This is a setting you may want to mess with. So 10 is fine, but with the Seestars, due to its small field of view, I usually lower it to the minimum, because if your frame doesn't contain many stars, it may fail to align them. So by setting it at the minimum, you'll make sure that even if your field doesn't have many stars, all the frames should register just fine. So now, since we have the two-pass registration option checked, what will happen when we click the Go Register button is that the registration process will be divided into two major steps. So the first step, as I've said before, is that Siril will detect the stars in all of the images, and then based on that compute the necessary data that it needs for registration and transformation, so the necessary data to align the images one another. But it is not going to apply the registration yet, so we are still working onto the same starting sequence. So since Siril now has written this new data, has evaluated the images, we are going to have some useful statistics to evaluate the quality of our subframes that we're going to do later in the plot tab and using the frame selector. So then, once we have evaluated our subframes and we have decided that we are happy and we want to apply the registration, we are going to get an apply existing registration option that we are going to click, and now Siril will create a new sequence with the registered subframes. As I said before though, these are mosaic frames. If we try to align them using the traditional global star alignment, most frames will fail to align, since many are taken too far from each other, so Siril can't find enough stars to overlap in order to align them all. We need a different approach. We need to use the Astrometric registration. Let me show you how. Go up here in Tools, Astrometry, Image Plate Solver. You'll see this menu. Here we will be able to plate solve our entire sequence in order to successfully apply a mosaic registration. In astrometry, in case you didn't know, plate solving is the process of obtaining an astrometric solution for an image. By comparing the stars detected in your image to a non-celestial catalog, Siril identifies exactly where the Seestar was pointed in the sky. So by using this method, Siril will be able to register frames also based on their position in the sky, providing better accuracy and flexibility if you have frames that don't all overlap with each other. As you can see in the plate solver dialog, the focal length and pixel size have already been filled in, and there's already the correct image scale right here, because Siril scans the headers for them. These parameters are also very important for plate solving, and in case Siril didn't fill them in automatically, try pressing the Get Metadata button, or compile the fields manually. The values you see here are valid for the Seestar S50, but make sure you look up the correct ones for the S30, S30 Pro, or any other rig. If you look at the catalog parameters area, you can see that the Gaia DR3 catalog has been selected, but the local catalog in my instance. It means that it is installed on my machine. By default, Siril will index the Gaia catalog online, so you don't have to download the index files on your machine. That's fine for operations that run on a single image like spectrophotometric color calibration, but when we have to plate solve thousands of frames, this will be slow and potentially clog the servers. So I recommend you use the Siril catalog installer script right here in Python script called Siril catalog installer, and you install this one, the Astrometric catalog. It is the optimal catalog for our purpose. It is roughly 1.8 gigabytes. Here you have the option to disable the auto selection of the star catalog that will be used, so you're free to use any other star catalog that you want, but the Gaia DR3 is chosen by default because it is the most comprehensive one, so I recommend you leave it on auto because it will choose the star catalog that is optimal for what you're doing for plate solving. Finally, you need to check Solve Whole Sequence. This is to make sure that every frame in the sequence is plate solved instead of only the currently loaded frame. So make sure that user registration information is checked. This is essential to make sure that the astrometric data that will be computed is going to be used as registration information to apply the registration later. Also make sure that these use coordinates from headers, all of these that say from headers that pull the information from the fits headers that I showed you earlier are checked because this helps the plate solving with useful information that makes it faster and more efficient. Okay, so now everything is all set and we can click the OK button to start the process. You can do this right now, but before that there's something I want to show you. It's optional, but it's useful to solve an issue that sometimes happens, especially with Seestar exposures, that too many frames fail plate solving due to suboptimal quality. So if you're getting this issue, you can attempt to solve it by going in Tools, Image Analysis, Dynamic PSF. The Dynamic PSF dialog is Siril's specialized tool for identifying and analyzing the stars in your image. This tool's underlying mechanics is fundamental to many core features of Siril, and this dialog is a way for us to access and tweak its settings. And those tweaks will affect the effectiveness of our astrometric registration, but also of other tools like deconvolution. First, we can click on the star detection button right here, and as you can see, it circled the stars it can see in the image and added them in this list. So it used orange circles for normal stars and purple circles for saturated stars, aka stars that are so bright they saturated our sensor. So they tend to grow larger in frame and may lose their color. It's normal to have some saturated stars in images, and Siril knows how to detect them. So this is way more than a mere star detection tool. It's also able to accurately model the PSF and many other parameters of the stars. The PSF standing for point spread function. Essentially, it's the mathematical function that describes how a star, that should in theory be a geometric point, is actually distorted and blurred by the atmosphere and optical system. This always happens in reality. Stars in images are never perfect points, and the PSF is essential to analyze and even attempt to revert the effects of this blurring. This process is called deconvolution. I'll briefly give a nod to deconvolution in the post-processing part of this video later, even though I'll then default to using a neural network-based sharpening tool, which is sort of a smarter deconvolution, we could say. What we'll use it for now is to make sure the image plate solver successfully solves all subframes. Default settings may work by only failing like 40-bit frames, but sometimes you may have issues with too many subframes failing to be plate solved. So you may want to look at this dialog. Usually the main cause for failed star detection in an image, especially for Seestar images, is elongated star shapes, or what we can call egg-shaped stars. So what we can do is to go here in the roundness threshold setting and lower it to something like 0.25 and then check Relax PSF checks. This makes sure that Siril is more tolerant towards stars with less regular, more elongated shapes, which is very common on Seestar frames and a prominent cause of issues with star detection. Then we could also lower the noise threshold like here, right here, which at default is usually set at 1, primarily to make sure that noise or hot pixels are not mistaken for stars. In my experience, it's generally safe to lower it to something like 0.5 to detect dimmer stars. So now we can click the star detection button again to test your settings. As you can see, it now detects more stars, 174 this time. This means that our settings are working by making Siril detect dimmer stars and also stars with more weird, more elongated shapes. So this is working, and of course you can tweak these settings further to further fit your star detection routine. In case, despite all of your tweaks, all of the settings that you have changed, a specific star still isn't detected by Siril and you want it to be detected, remember that you can always draw a box using your left mouse button around the star, right, like this. Then right click and select pick a star. And if within the box that you have drawn there is an object that Siril recognizes as a star-like object, then it will be added to the list and Siril will analyze it and treat it like a star. Let's pick up our image plate solver again and click OK to start plate solving all of the sequence. Okay, so now our frames were plate solved. Almost all succeeded, so this is a very good thing. So now, since our frames have been plate solved and analyzed, we can go into the plot tab to inspect our frames based on their quality and decide which frames we want to reject and which ones we want to keep. So now let me give you a quick overview of the main parameters that we are going to use to evaluate the quality of our frames using the plot tab. The first one is FWHM, full width at half maximum. Simple definition first, it is a measure of how big the stars appear in your image. In this case, it is being measured in pixels, but remember that you can always switch it to arc seconds in case you also want to compare it empirically to other optical trains that have different resolution. For the Seestar right now, to compare our datasets, we are going to use it in pixels. So, as you can see, we have values that range from 2 all the way to 6.42 in FWHM. So, as a general rule, values that go from 2 to 3 FWHM are very good. From 3 FWHM to 4.5, they are good but mediocre. And anything above 5 is bad, so I usually reject anything above 5, and from 4.5 to 5 it is mediocre, or you may want to reject it as well. So usually the rule is the lower the better, so it usually means that when you have a lower FWHM value, the stars are smaller, and so it means usually that they are in better focus, they are less soft, better focused, as I said, and when the FWHM value is higher, the stars are more big, they appear bigger, they occupy more pixels, therefore they are softer and usually in worse focus. So there's also to note that although the general rule that I said is the lower the better, if you add, for example, values of 1 FWHM, so 1 pixel FWHM, then that isn't a good thing. It means that your system is severely undersampled, and so that if a star tends to take 1 pixel, then there is that issue. This usually doesn't happen with the Seestar, even though it is undersampled, just not severely undersampled. So you can already see it in the graph right here, that on the x-axis, now quickly let's see, on the x-axis we have the number of frames. You can change this, but this is the default visualization. Right now you can see we have the number of frames here, and on the y-axis we have the value of FWHM expressed in pixels. So here we have frames that range from 2 FWHM to 6. But quickly, let's go to the next value, which is roundness. So roundness instead is a measure of how regular, so therefore the name says it, round your stars are. So here it is that the higher the value, the higher the better. So the values that are closer to 1 are stars that are rounder, are more circle-like, and therefore they have a more regular shape, which is a better thing. While values that are lower are stars that have a less regular, less circle-like shape, and so therefore they tend to be more elongated, and this is extremely common with the Seestar. You can already see that the values here are already all over the place due to the tracking errors that the Seestar makes, since it is not a very precise mount. It doesn't have very precise tracking. So we're going to see this later again. So the next value, the next parameter is background. So this is pretty self-explanatory as well. This is the brightness of the background. And so you can use this to measure your light pollution if you are comparing frames from different bottle, from different skies, or maybe you have frames with the moon, you want to compare how much impact it had, or what it is very useful for in this case, the background parameter, is to catch frames that have had some sort of interference like clouds or flares from other lights, so it is useful for this mainly. So the next is the star count. This is simply a parameter that shows you the number of stars that Siril was able to detect in each of the frames. So now let's explore the plot tab with each individual parameter. So now we have the FWHM parameter set as the y-axis. We can see that we have frames that go from as little as 2.10 FWHM all the way to 6.42. So this is a pretty big variation, so we have a pretty good number of frames that I deem blurry and that I would reject. If I were aiming for a better sharpness in the image, I'd probably reject anything above 4 pixels in FWHM, although of course this also depends on how aggressive you want to be with rejecting your data, what's your quality standards, if you want to get an absolutely sharpest image, or you're willing to be more tolerant just to have an image with more signal, with more frames stacked. So in this case I'm going to be more tolerant because this is not a lot of frames, especially for a mosaic, so I want an image that is less noisy, more usable in terms of signal. I'm not aiming for the best sharpness here, so just keep it in mind that the values that you start rejecting from are not universal and they depend entirely on the context. The first way to browse the frames and reject them is to go again, open the frame list. You can do this from here. And as you can see, there is this column, the column FWHM, that in the frame selector you'll get the value of whatever parameter you have selected here for the plot. So now we can browse them and we can see the value. If you click the FWHM, now they are in ordered from the lowest to highest. Okay, so now let me show you, for example, the frame with the lowest FWHM value so you get an idea of how they look like. So this is the frame with the lowest FWHM value. So this is among our sharpest frames in the whole sequence. So as you can see, even the central stars of the cluster that are pretty bright are not too big. All the stars are pretty small. They look pretty sharp, as you can see. So this is there isn't even a lot of aberrations, so the stars look pretty normal. They don't have weird shapes. So this is a very beautiful frame. If only all could look like that, but this is not possible. So if we go to all the way down, we can select the frame with the highest FWHM value. So let's select it. And as you can see, it looks much different. The stars are bigger, they are bloated, and they look soft. They are blurred, they are very visibly blurred. So now, since this is a mosaic, let me add this detail so that this green box that you see is basically that is added to when you browse the sequence, and which is always visible. Is simply a way for you to understand where the frame is positioned compared to the reference frame of the sequence, which is going to be the center of your mosaic. So if you scroll, you should see a frame that is highlighted. Siril automatically chooses it. So usually Siril for mosaics chooses the first frame. As you can see, the index is 1. So this is the reference frame. The green circle is the center of your mosaic, and for reference it is going to be shown overlaid on every frame to make you understand where it is in space, where it is compared to your reference frame. Going back to including and excluding your frames using the frame selector, you can go into the check icon and uncheck it like this, and it'll show an X to tell you that it has been excluded from the stack. You can re-include it. You can also do like you would on a file manager, so shift click selecting a bunch of frames and using this check icon to all select or exclude them all at once. So you can also use this button in case you want to reset your checks. So you want to reset the list that in a way that it includes all frames again, in case you want to start from the beginning. But as you may understand, this is a bit tedious, so this is where the plot tab comes in handy. So if you want to use the plot tab to, for example, like I said before, reject all frames above 5 FWHM, you can go onto the plot tab and then drag using the left mouse button and draw a box like this. So the box here will show you the number of frames right here that have been selected, also the minimum value of WHM that the selecting box includes, and the maximum value. So as I said before, I want to reject all frames above 5 like this. So let's drag it to 5. And 116 frames will be rejected. If you if you right click, it will show you a few options like excluding the selected points, so the selected frames that you want to reject, or choose to only keep the points within this within the selection. So you can do both. I usually exclude the selected points. You can click on it. You can also draw a selection to zoom in on a specific part of the graph. It'll show the lines, so every line in this visualization is a frame. So if you want to go onto the plot and view a frame, you can right click on the line and either exclude the frame or show the frame using the frame list. So to go back to the normal zoom level, you can just double click like this. So since now I'm happy with the FWHM values in my sequence, we can go onto the y-axis selector and switch from FWHM to roundness. Roundness being, like I said before, another very important parameter for the sharpness of the final stacked image. And looking at this plot, we can immediately see that it tells us something very important. As you can see, the values go all the way from 0.85 to 0.50. It is extremely irregular. If this data came from a higher hand tracking mount with guiding, you'd probably see that the roundness, the plot would mainly show lines from 0.8 or more, and they will be mostly exist regularly. For example, the box that I've drawn, so they look pretty regular and stay within a good roundness threshold. With the Seestar being, especially with this data in altitude azimuth mode, it is absolutely not the case. The Seestar makes very frequent tracking errors and trailing, so the values are extremely inconsistent. We can always right click on one of the worst frames according to the roundness parameter and show you how they look like. So let's choose, for example, this one, which is even worse. So based on what I see, the stars don't even look that big. The FWHM value probably isn't that bad. But as we can see, the stars are significantly trailed, and this is why it has a very low roundness value. And so this indicates that the Seestar here made some very obvious tracking error, and so these frames are the ones that have the worst roundness. If we went to select the frames that have the best roundness to compare, we're going to do this on the top of the graph, show frame, and look at the difference. The same stars here look much more round. They are not egg-shaped, they are not irregular across mostly all the frame. They are very round, very regular, and have a good sharpness. They are not too big, so this is a very good frame. Another very cool thing you can do in the plot tab is change how the graphs visualize your data. So for example, here at default, the x-axis is set to show the index of the frames, but you can change this, for example, to FWHM to, for example, show how the FWHM and roundness parameters are related to each other somehow. Even though they are different and measure different things, they are still somewhat related both to the shape and size of the stars. So you can immediately see that frames that have higher and so better roundness values also tend to have lower FWHM values. So you can switch between a few parameters and get these cool scatter plots that can help you visualize your data in other ways and also make more informed decisions on calling your data. But for example, also help you see that this is not a universal rule, because you can still have frames with good roundness values but higher FWHM. And this is one of the biggest problems that you'll face when you pre-process Seestar data, is that you'll see that many frames are more than suboptimal for sharpness of the final stack. So of course what you want to do with the frames still depends on what you want to do for the final stacks. If you wanted an absolutely sharp final image, you probably could do something like always drawing a box like this and selecting all frames under 0.68 roundness, and you would reject a massive amount of frames like here 925. This will do a big difference in terms of sharpness. But also here, in my specific case that I show you right here, I want to make sure that the final image that I get from this stack is not too noisy, since this is not a lot of data, and so rejecting these many frames will not be very good for my objective today. So just for demonstration purposes, I probably only reject frames above 0.59, so the absolutely worst ones. In practice, this is not going to do a very big difference to the final image, but it is for demonstrations. Because also keep in mind that since the Seestar makes many short exposures, if you reject 10 to 20 bad frames, in practice it is not going to do a visible difference to the final stack, because being so many frames, even if some bad frames slip through, they are going to be averaged out because the frames are so many. And so the reality with Seestar data is that if you want to noticeably improve the sharpness of your final image, especially with so many suboptimal frames, you're going to want to reject not tens, but hundreds, if not thousands of frames, depending on how large your dataset is. An example where culling your data aggressively could make a huge difference in quality is if, for example, you have 60 hours of data on a small galaxy like the M51, you could reject 10 or more hours worth of frames to only stack the sharper ones. And so you can make your final image much sharper if you're looking for finer detail, with a very long exposure time, so you have way more headroom for rejecting bad frames and not losing a lot of signal. Let's also give a look to the background plot. So immediately we can notice that there's frames that start from a lower value, then it peaks suddenly to a higher value, then it goes low again, then it peaks again, all this way to the end. And I can immediately tell that this is expected behavior, since the peaks happen later into the night, when the Rosette Nebula is setting towards the west, and so it's close to the horizon and the light pollution is higher. And so this is exactly what you'd expect to see. Usually what you want to look for in the background, with the background parameter in the plot, is if your frames follow a consistent consistent values. So if you have a consistent graph that doesn't show any anomaly. So if you had to have, for example, a mostly consistent flat graph, and then a random peak in the middle of it that seems inconsistent with the rest of the data, then there you'd have a problem. So the most likely culprit is clouds or lights getting into your frames. So for example, here now I've selected a frame that has is on the lower end of the background value, and there's no issue with it. So make sure that you also check your frames. So you, for example, there's this peak, but then there's this random higher peak right here. This looks inconsistent. Let's zoom in. There could have been a cloud or something passing by. You can't always tell because the clouds sometimes blend in, but make sure that you look at your frames like this, you blink them. I think there was a cloud, but the frame was inconsistent, so we can reject. It's 3 frames, so let's exclude them. Then here there's this higher peak. Even these frames are probably closer to the end of the night. There could be clouds. You have to look carefully here, so you have to blink your frames and compare them to the others and just see if it's some extra light pollution that comes from the nebula being towards the horizon, or clouds, which is what you want to mostly look for. And to do this, you can also configure it this way by doing the stars and background scatter plot. So you can look for frames that have the least amount of stars and the highest background values, and you should inspect them. For example, this one right here is also trailed, so it's a bad frame in general. This one really looks like it had some sort of cloud in it, so you can reject this kind of frames always like this. Now that we have inspected our frames and rejected the poor ones, it's time to apply registration by going into the drop menu and selecting Apply Existing Registration. Make sure that the framing method is set to maximum and not current, because current will only, the stack with the current framing method will only be the area of the reference frame. Maximum will have the area of the entire mosaic, so of every subframe. You can also click estimate, and this is roughly how large the output image should be. So finally, if you hit go register, Siril will create the new sequence with the registered subframes. Basically, it is going to duplicate every frame from the current sequence, but with the registration applied, ready to be stacked. And they are going to have the prefix R, so you can go into the home directory to see the new registered intermediate files. So also check your disk space over here to make sure that while the new sequence is being created, you don't run out of storage. So you can apply the registration right now if you already trust your settings. If you don't, please follow along. Looking down here, you'll notice that the Drizzle option is selected and locked. You cannot change it to interpolation. That's because we didn't check the Bayer when creating our sequence. Drizzle is the variable option because it will reconstruct the full color image by itself. But before we apply it, let's understand what Drizzle is. Drizzle is a reconstruction method used to recover spatial information from multiple lower resolution dithered subframes by mapping every pixel of the input images to a finer grid in the output image. So if it's not immediately clear from this definition, don't worry, I'm going to break it down. First of all, dithering is the process of slightly moving your mount in between exposures, and the Seestar does it automatically. More on why we need the dithering later. So, Drizzle takes all the input pixels in the exposures. Think of every input pixel as a droplet. So Drizzle figures out exactly where on a finer output grid those droplets should land on. Compared to interpolation, the method that you would have used if you had checked the Bayer, Drizzle preserves sharper PSFs and more accurate color information, at the cost of increased noise in your image due to how the pixels are redistributed on the finer grid. So, in order to benefit from Drizzle, make sure you have a decent amount of data. Try to aim for 6 to 10 or more hours if you want to use Drizzle comfortably. Also, for mosaics, definitely account for your total integration being spread across the whole mosaic frame and each panel having less than the total amount of frames suggests. So, here's the thing. There are two very big advantages of applying Drizzle on Seestar data. The first, and probably major one, is better demosaicism of CFA images, and the second one being a better reconstruction of fine detail in undersampled data. So let's examine both advantages. The first advantage being what we can call a Bayer Drizzle. So do you remember about the Seestar having a one-shot color sensor? Because of the color filter array, a CFA, any given pixel physically records one color. This means we literally have holes in our data. We are missing color information across the image that has 3 channels, red, green and blue in the final image. So, for example, if interpolation has to decide the value of a red pixel across all 3 channels, it has plenty of data for red, but it has to guess the blue and green values by averaging the closest neighboring pixels. This guesswork is the source of less accurate color and blurring of fine detail, since this process tends to smear the detail. Drizzle, on the other hand, assisted by dithering, uses the sub-pixel shifts to fill this hole with real measurement from all the appropriate color pixels. So this is one very big advantage and one that makes a very noticeable difference on CFA data. And in order to benefit from this, you don't necessarily have to upscale. A one-time Drizzle is great on CFA data most of the time, while making it easy to keep the noise level acceptable, accounting for the effective color data coverage of a CFA image. The other advantage is for undersampled data, because the sensor inside the Seestar is undersampled compared to the optics. In the Seestar's instance, the sensor and optics have roughly the same resolution of 2.34 arcseconds. This seems good at first, but that's a common point of confusion, so let me clear this up. If we go by the Nyquist-Shannon theorem, you ideally need 2 to 3 pixels to accurately sample the smallest detail your optics can resolve. For example, that could be a very small star that matches the telescope's image scale. So if one pixel matches your telescope's resolution, the star will look like a square. To fix this, Drizzle uses the sub-pixel shifts provided by dithering to capture different information about the same detail in every frame, just how it does for colors. The algorithm then takes all these input pixels, turns them into droplets, and rains them onto a finer output grid with more pixels, figuring out where each is supposed to land, effectively upscaling the image. This is if we have set a scale larger than 1, that is. Enough with the talking, let's look at the actual settings. At first, we have the scaling. If we leave it at 1, the final image is going to have the same pixel resolution as the input images. As I said, this is great for most cases if you just want to improve the sharpness and color accuracy of your CFA image by avoiding interpolation. You may consider values larger than 1, so for example 1.5 or even 2, in case you also want an image that better reconstructs finer detail and small stars. So if you are working on small galaxies like M51, where a few extra pixels could be advantageous. Though, always remember that Drizzle isn't magic, and it will not give you any extra detail that your optics cannot physically resolve. So, for example, setting your scale to 3 is going to give you little to no real gains in detail. It's mostly lots of noise and a huge file size. Of course, this also depends on your equipment. The Seestar has its limits, and it usually does not benefit from huge increases in resolution. If you upscale, setting anything larger than 1, your data is naturally going to be spread over more pixels, requiring more integration. In my experience, 1.5 is a great compromise for the Seestar. It gives you a 125% increase in total pixels, and only twice the file size of intermediate registration files, as opposed to 4 times with a scale of 2. The Seestar can support and benefit from 2 times Drizzle as well, since it gets you closer to its theoretical resolution limit, but it's often a marginal improvement compared to 1.5x. This is the pixel fraction setting. Pay close attention here, as understanding this setting is crucial in order to use Drizzle correctly. Remember how I said Drizzle treats the input pixels as if they are droplets, hence the name Drizzle. This setting lets you fine-tune how big you want the droplets to be. The lower you set pixel fraction, the smaller the drops will be. So the pixel area each drop covers in the final image is smaller, meaning that you get a sharper reconstruction of fine detail and noise that is less correlated and more randomized. More on this later. On the opposite end, with high values, since every drop is bigger and covers more area, it means that you get an image that looks smoother, but with more blur, and fine detail that is less sharp. As a common rule of thumb, Siril's documentation recommends setting pixel fraction as the reciprocal of your scale. For example, if you set 1 as scale, you'd be looking at a recommended value of 1, as it's already set here as the default. For a scale of 2, since the output pixels are half as tall and half as wide than the input pixels, you'd be looking at a recommended value of 0.5, meaning the droplets are half the input pixels, the same size as the output ones. This rule makes sure that your droplets are exactly the size of the output pixels, not too small nor too big. If your pixel fraction is too big, you'll get more blur and correlated noise. If it's too small, there may not be enough droplets to cover the whole image. However, the Seestar is a special case here. Since it easily produces thousands of short exposures, holes in your data are very unlikely. You have excellent coverage throughout all your image, meaning you're free to experiment with lower than reciprocal values to see if you can get a sharper image and less correlated noise. For this rosette data, I'll use a scale of 1 and a pixel fraction of 0.8. Since the output image will have the same number of pixels, this means the droplets are slightly smaller than the output pixels. This is the droplet model, so the shape of your droplet. It's set at square as default, since it preserves the flux of the stars and makes it more accurate for color calibration. Some model that works well with most images, so it's the one that is set as default on Siril. So let me show you some visual examples using this IC434 stack. So this is the interpolated stack, this is the Drizzle stack. So the first thing that you can see by switching between the two images is that the noise profile is dramatically different. The drizzled image looks more noisy, but the noise itself, as you can see here, it's finer. So the point here is that, as you can see, the noise in the interpolated image is not random at all. So let me cycle back and forth a few more times to show you better. The noise in the interpolated image forms all of these structures. It is very structured. How can we call them? It forms all of these worms. Yes, I think that's a good way to describe it. So these blurry clumps of noise that look like sort of structures but are not. And so this is also, as you can see, it is blurry. The image itself, the detail compared to Drizzle is blurry. So the thing here is that you may struggle even in the interpolated stack to tell what is signal and what is noise because of all of this mess in the noise profile. And so the same thing happens to denoisers like Graxpert that suffer a lot with correlated noise because they are not exactly able to tell what is detail and what is noise, so they start hallucinating on all of these patterns in the noise by hallucinating small stars or small detail that actually isn't there because they think they see something in the noise. With Drizzle, however, this becomes much less of a problem because the noise being more randomized, it suddenly doesn't form anything that looks like detail in the background. So even though the signal per pixel may be lower due to how Drizzle works, so even though there may be more noise visually, it is actually easier to remove this noise because it is less correlated. Okay, so now that we have put our settings, everything is set up, we can finally click onto the Go Register button from Apply Existing Registration and watch as the registration is applied. Okay, so now that our registration has been completed, it has been applied. Now a new sequence with registered subframes has been created and automatically selected by Seol with the sequence with the prefix R. So now if we auto search and look at these subframes of this new registered sequence, you can see that they look weird. They have all of these patterns, and this is completely normal, a normal intermediate step of the Drizzle process. So don't worry about them if they look weird because they look normal at the end of the process. So now let me also show you what happened inside the SEO home directory. Now we find the previous starting sequence, but if we go down, we can see that there's these new files, the new registered sequence with the registered subframes. If we go up here again, you'll notice that also this folder was created that contains other temporary files of the Drizzle process. Again, you don't have to open this, you don't have to understand exactly what they do. These are simply intermediate files that the Drizzle process uses. Just keep in mind that they'll be taking up quite a bit of storage, as you can see right here, so just make sure you have enough storage. Finally, with the registered sequence, we are getting to the final part of our pre-processing. This is the stacking tab. Now let me guide you through the settings. First of all, the method that we are choosing is average stacking with rejection. So average stacking simply outputs the mean of all the pixel stacks in the image. It is the go-to for stacking your light frames, improving signal to noise ratio while allowing you to normalize your images and reject outlier pixels. More on this later. Next, we have denormalization. So before we select an option, let's see what normalization is in the first place. So average stacking works best when the images are all statistically comparable to each other. But this means that things like different light pollution levels make this more problematic because the image is going to have different background brightnesses. So normalization brings frames to a common background brightness and signal level, so pixel statistics are comparable across the stack. Basically, normalization makes sure that the histogram of all images are somewhat matched to each other. This is especially important for pixel rejection to work correctly. For light frames, additive plus scaling is recommended, so it is already selected. And additive means that it adds or subtracts from the background's mean brightness to match all images, while scaling tries to match the signal. Then, very important, we have pixel rejection. So that is what's going to clean up our images of any outlier pixels before arranging them. Basically anything like satellites, odd pixels, cosmic rays, basically anything irregular, so that it does not show up in your final image. Out of all methods, we are looking at two specifically: Windsorized sigma clipping and linear fit clipping. The difference between the two is in how they measure the outliers. Windsorized sigma clipping looks at the individual pixels across all images and establishes the standard value it should have across images. And basically it says if this pixel differs more than a certain number of sigma units from its standard value, then it is definitely an anomaly. So for example, if such pixel is hit by a satellite or a plane, it'll have an abnormal value. Linear fit clipping, on the other hand, takes into account that the pixel stacks will change a bit throughout frames, due to gradients and different light pollution levels and many other variables, meaning that it performs very well on datasets with more complex gradients. So what it does is that it fits the best straight line of the pixel stack, and only reject those pixels that are far from it, while Windsorized sigma clipping may mistake more pixels for outliers. Linear fit clipping is excellent for large datasets. It is perfect for the Seestar since we have more than 2000 frames here, meaning it is likely our best choice. So as you can see here, both algorithms allow you to set a low and high value, and basically this allows you to fine-tune how aggressive you want the rejection to be. So I found personally that starting with the default settings that you have in both is fine in my personal experience though, because I don't usually get satellites, trails or odd pixels. Also because across thousands of frames, averaging alone tends to fade out some extreme outliers on its own. But you can always change the settings. Also, you can check create rejection maps right here. It is a good choice to look at your rejection map, so you can see what is being. You'll get an image that shows you what is being rejected. You'll see all odd pixels and satellites, and you can also verify that none of the real signal, like the structure of your target, shows up in that rejection map. And if it does, you may want to tweak your low and high settings. Then, if you want, but it is also recommended, you can set a weighting method. So a weighting method allows us to assign a different weight to each frame, aka make it so every image contributes more or less based on the weighting method that we used. If we use weighted FWHM, then frames with a lower FWHM value, therefore the sharper frames, will have a higher contribution to the final stack, while blurrier frames will contribute less. Noise, instead, gives a higher weight to images with lower background noise levels, as opposed to the sharper ones. So as you can see, there are other weighting methods like number of stars or number of images, but in my opinion, weighted FWHM and noise are the best all-rounders. Especially weighted FWHM. It is good in many situations, since it also takes the numbers of detected stars into account. So even if a frame is sharp, but it's covered by clouds, it'll have less weight. Noise weighting is good if you're trying to get a less noisy image instead. So which one you choose is really up to you. I will choose noise weighting just because, again, this is a 2x mosaic, only 10 hours, so this data is a bit limited. Since we use the mosaic registration, you may also notice that we have some extra settings. We have feathering right here. This applies a smoothing mask on every image over whatever number of pixels you have set to make sure that there aren't hard seams between them. This is very effective if you already have pre-stacked panels you want to build into a mosaic. Generally though, with Seestar mosaics, you don't really need this option because you're building the mosaic from individual subframes and the results are usually smooth on their own. However, you should still try out this option if you happen to get hard edges. You also have this normalization on overlaps setting that helps get a more consistent result in case your panels have little overlap or if they exhibit noticeably different characteristics due to the differing nature of the targets over your mosaics or differences in capture at the expense of slower stacking. This feature, however, is intended for stitching stacked panels, not for individual subframes. So for Seestar subframe mosaics, you should not be using this option. Okay, so all options are set, and make sure that you double check them before you stack. Make sure that you're using the settings that you want and that you're stacking the images that you want. So right now we can see right here that all of our 3000 images are going to be stacked because they are in the sequence that we have created after applying registration. So this is fine. Optionally, you can also add these filters. For example, for FWHM, stack only the 90% best images in FWHM, and it'll tell you how many images are being stacked if you select more filters. You can do this, but I'm not going to do this since we did our rejection. We did them earlier in the registration and plot tab. So I'm going to have no filters here and I'll double check everything, so like the name of the stack and the overwrite option. That means that if you decide to stack another time, then the previous file will be overwritten. So what are we waiting for? Let's click start stacking. It'll first show a progress bar telling that the normalization is being computed, and then the longer part is going to be the rejection stacking that comes later after that phase. Okay, so stacking is complete. Depending on your hardware, this can take anywhere from a few minutes to almost an hour or more. Mosaic stacking and Drizzle do add up a little bit of extra processing time. So usually, after you're done stacking, Siril will automatically load the stacked image into the image area. Also, you can absolutely load it from the home directory by dragging and dropping the image into the image area, or using the open button and navigating into the directory where your image has been saved, or also clicking onto this arrow to open the list of recent images in case you have loaded the image before. So now let's auto stretch the image. Now you'll notice that the whole image has a heavy green tint. Do not panic, this is totally normal. Your RGB channels are just currently unbalanced. We'll fix it later. For now, to optimally visualize it, untick the chain icon near the auto stretch button to turn the stretch from a linked stretch to an unlinked one. This is ideal to visualize the image in the first steps of post-processing. Now you can also see that as a result of the mosaic stacking, we have black borders. Also, the area of the stack is affected by field rotation since this is Alta's data. So what we want to do now is to crop the image to make sure that we have none of these black borders. To crop, you simply want to hold your left mouse button and draw a box of the size of the area that you want to crop in. And then right click to access the context menu. Go into crop and click crop. Now the image has been cropped. Now you can change from auto stretch to histogram to apply an extremely aggressive stretch that helps you spot what to leave out of the image. So what you're looking to leave out is, for example, areas with more noise or art seams, for example, due to the different coverage that each area gets. Since this is a mosaic, you'll notice that the very outer edges have more noise and a bit more gradient, so Seestar mosaics are a bit messy like that. So you want to crop those areas out and only leave the the center area that has the most coverage, the most consistent signal. So we are gonna do just that. Also, one of the very first things that you'll notice is that the image has a gradient in the background, mostly caused by light pollution, the moon, or other factors. Gradients can be more or less complex depending on the conditions and the data. In this case, we have a pretty prominent circular gradient on the outer areas of the image. This one is pretty weird looking. If you didn't have a mosaic, you'd probably have a much simpler gradient. I think this is just a consequence of the subframes with different background brightnesses being stacked into a mosaic. That's likely a reason. But honestly, there could also be something that I'm missing here. In fact, if you happen to see harsh gradients or seams that in this image I don't seem to see, make sure that you inspect and exclude the possibly cloudy or obstructed frames first before you try correcting the gradients in post-processing. I'll now show you two ways to do a gradient removal or background extraction. So first, a fast but mediocre way called Graxpert, and the second being a slow but most precise and generally preferred manual background extraction. So first, let me show you Graxpert. Go into Scripts, Python Scripts, Processing, Graxpert AI. So first thing you want to do is to make sure that via the Graxpert model manager that your background extraction models are downloaded. If you haven't downloaded them, you can select them from here and download the selected models. Make sure that the operation is set to background extraction. So the first setting that we see here is the smoothing, and just like the name suggests, it controls how smooth your final result is going to be. So higher values produce smoother results for simpler gradients and better preserve real structure, while lower values are better against complex gradients but can easily be more destructive and also take some real structure with them. So for this image, I think I'm going to leave it to somewhere like 0.5 or even 0.60. So then we have the correction type, which is set as subtraction, or you can also set it at division, but for traditional background extraction, let's leave it at subtraction. You simply click apply, you give it a little bit to run, and as you can see, it did its job. It did it pretty well. We can also undo the operation and redo it to see what it did, maybe also histogram stretch it. So Graxpert does a very good job. It is great at removing gradients, but while it removes gradients, it can also easily remove structure with it. Graxpert can sometimes be pretty destructive to the data in your image. So especially as you can see in the comparison that I'm showing on screen right now. It is not always a problem, but sometimes it can really be destructive. So that's why usually I prefer to do a manual background extraction via the background extraction tool in Siril, because it allows me to have more control over the process. Okay, so let me show you how to actually use it. So the first setting that you can see here is this drop down where you can select the interpolation method. So RBF is currently the most modern method that works well with complex gradients. With RBF, you only have the smoothing parameter, which is very similar to what Graxpert does. That calculates how smooth the transition between the sample points that I'm going to show shortly is. So the other method is polynomial, which is simpler and usually good for removing gradients on individual subframes, for example, because they tend to be very simple. If you were to left click in your image, you can see that you'll place a square. This is a sample. Everywhere you're placing this in the image, you're essentially telling Siril, hey, this is background. Multiple samples placed in different areas of your background are able to model the gradient in your image. This means that generally you want to place your samples in areas of your image that you think are quote-unquote empty background. So, which means an area where there is no visible or faint nebulosity or no structure. So, where you think that there is mostly just a gradient or sky glow that you can effectively model, that you can sample. So, you can place the samples manually, as I showed you. Then you can, or you could also click the generate button, and Siril will place some samples automatically for you based also on the settings in the dialog. But you can see that there is a bit of a problem with the way Siril has placed these samples. As you can see, many ended up directly onto the nebulosity, and if we were to compute the background, so this is just a preview that it is applying, you can easily see, if we also show the original image, that some real signal is being removed. That's because it is like if we place samples on our nebulosity, we are basically treating some of this structure as if it is gradient to be removed. So this means that we have to change this. So at this point you can start placing your samples manually, or you could try, for example, lowering the grid tolerance all the way to the minimum, hit generate again. So you can see that this looks better. There are less samples directly onto the nebulosity, but this still can be improved. So you can switch to the histogram stretch to see more of the faint nebulosity in the background. You can see that some samples are still placed onto the nebulosity. So for example, you can right click to remove the samples that you want to remove. But also, I think that 20 samples per line is a bit much. You generally don't need all of these samples all across your image. You need just enough to model the gradient in your image, because the more samples you have, the more you risk accidentally including your nebulosity. So you could lower this to, for example, 10 samples per line. This is an example of how I've placed my samples. With smoothing at 0.5, I think it did quite a clean job, showing you before and after. I tried my best, trying to avoid all of the fainter nebulosity, but of course it may not always be perfect, and that's fine. There are some targets where finding your background can be very hard, or almost impossible without including at least some nebulosity. In those cases, you should try to place your samples in areas with the least amount of structure that you can possibly see and that is consistent across your samples. On some difficult targets like this, you may be tempted to just throw Graxpert at it, but if you can take some extra time to carefully select your samples, the results will likely be superior. Do not forget to click Apply, and now your gradient removal has been applied.